Hello everyone and welcome to the Funny Documentary Channel. Tonight, we'll be exploring a gently fascinating question. How far can the James Webb Space Telescope actually see into the universe? Now before we drift into tonight's quiet journey, take a moment to like the video, subscribe to the channel, and if you feel comfortable, leave a comment sharing when and where you're listening from. I always enjoy seeing those peaceful check-ins. Someone winding down after a long shift, someone listening from a cozy bedroom, someone halfway across the world letting these soft stories carry them into sleep. So, settle into whatever is holding you. Let your breath stretch a little longer, and let's begin this quiet exploration together. Chapter 1. When the Early Universe Refused to Behave. In the quiet years before the first images arrived, astronomers often described the early universe the way a hiker might imagine a distant mountain valley. Beautiful in theory, largely uncharted, and almost certainly empty. The predictions weren't guesses pulled from thin air. They were the product of decades of simulations and hard-earned observations. Everything pointed toward a cosmic dawn that unfolded slowly and delicately. Galaxies, according to this well-behaved picture, would begin its tiny, tentative gatherings of newborn stars. Light would trickle out from them, soft, sparse, and faint enough that only the most sensitive eyes could hope to detect them. And for a long while, that story felt stable, calm, comfortably predictable. Then came the first deep fields from the new telescope, those silent snapshots taken during its earliest days of science operations. The images arrived without fanfare at first, tucked inside data files that only a few research teams had access to. But as the teams began to stretch the light, peel apart wavelengths, and examine every smudge, a strange pattern started to emerge. A pattern no one was prepared for. There were galaxies everywhere, bright ones, compact ones, some so distant that their light had set out across the cosmos when the universe was barely old enough to know what gravity was. And yet, there they were, clear, confident points of light standing where the textbook said only the faintest glimmers should exist. Astronomers have a professional tone they use when faced with unexpected results. It is polite, measured, and often accompanied by long pauses between words. That tone permeated the early discussions. Observers double-checked exposure times. They reran redshift estimates. They verified calibrations with a level of caution usually reserved for disarming ancient artifacts. But the galaxies didn't vanish. If anything, more of them appeared the longer the teams looked. The early universe, it seemed, had not shown up to the first day of cosmic evolution with the proper paperwork. Instead of offering a sparse scattering of tiny structures just beginning to assemble, it looked alarmingly busy, as though entire neighborhoods had sprung up overnight, fully illuminated and already bragging about their star formation. A few researchers joked quietly that the cosmos had apparently skipped several chapters in its own origin story. The atmosphere in the research community shifted almost immediately. What had begun as a gentle anticipation, the expectation of discovering faint whispers of starlight, turned into something more unsettled. Curiosity gave way to recalculation. Confidence yielded to caution. Teams that had spent years preparing search strategies suddenly had to rewrite the early universe section of their notebooks. Not because the universe contradicted the theories outright, but because it confidently sidestepped them, as though unaware that human beings had devoted entire careers to predicting what it should have been like. The density of bright candidates held particular weight. Astronomers had expected to see a handful of objects at extreme distances. Instead, some deep fields looked like crowded train stations at dawn, full of motion and structure, busy in a way that felt almost impolite for an epoch so young. Each new detection hinted at stars forming faster, galaxies assembling sooner, and the cosmic landscape blooming with a vigor no one had anticipated. Some researchers, exhausted but impressed, remarked that it was fortunate the universe did not have access to the grant proposals submitted over the previous decade. Otherwise, it might have realized it wasn't supposed to build luminous galaxies so early and adjusted its behavior accordingly. What slowly replaced the initial surprise was a deeper, quieter recognition. The early universe was not the fragile, tentative place it had been painted to be. It was energetic, efficient, restless even. Light didn't merely glow, it surged. Structures didn't stumble into existence, they gathered themselves with startling decisiveness. This realization didn't break cosmology. It simply reminded scientists that cosmic history is not built to satisfy expectations. Instead, it unfolds according to its own internal logic, one that human beings glimpse only in fragments filtered through instruments, models, and the patience required to interpret them. And so the first chapter of this unfolding story is not a tale of failure or contradiction, but of humility. A reminder that the universe did not sign off on our predictions. It never promised to behave in ways we found intuitive. It simply offered its light, ancient, unhurried, and abundant, waiting for someone patient enough to unveil it. The early universe, it turns out, was never empty. It was merely waiting to be seen. Chapter 2. The night, the numbers, didn't make sense. There are moments in science when numbers behave like mischievous spirits, appearing reasonable at first glance, then revealing themselves to be slightly absurd when examined closely. For astronomers studying the earliest galaxies with fresh JWST data in early 2023, this moment arrived not with fanfare, but with a quiet ping from a computer terminal. It was the kind of notification that normally meant routine progress, a data reduction finished, a photometric estimate generated, a model converged, nothing dramatic. But the numbers it contained were dramatic. In those first weeks of deep analysis, researchers began noticing candidate galaxies that had no business being as massive as they appeared. These weren't the gentle, octentative infants that cosmological models predicted for the universe's first few 100 million years. They were big, bright, suspiciously mature. Some seemed to rival the Milky Way in mass, despite forming at a time when the cosmos should still have been stretching its limbs, blinking awake in the dawn of creation. When the team led by the astronomer Ivo Labbé began studying these objects in depth, the mood shifted from curiosity to concern. It wasn't that the galaxies looked wrong. They were perfectly ordinary in shape and brightness. They simply existed far too early. In the cosmic timeline, a galaxy the mass of the Milky Way, barely a few 100 million years after the Big Bang, is like spotting a fully grown orchard beside a seed that was planted yesterday. You don't question the apples first. You question your calendar. Labbé himself later described the moment of recognition with a tone that blended awe and bewilderment. After carefully analyzing one galaxy that appeared impossible under standard theories, he found another with similar characteristics. Then another. Then, in what must have been an increasingly surreal sequence of clicks, several more. By the next day, the team had identified 6 candidates that defied expectations. Finding one impossible galaxy is alarming. Finding 6 before lunch feels personal. The results spread quickly across the astronomy community, surfacing in messages between collaborators that carried an unmistakable mixture of excitement and dread. These weren't the small, delicate structures predicted by decades of modeling. They were enormous, bright, and surprisingly well assembled. Their estimated masses suggested star formation on a scale and at a pace that was difficult to reconcile with established theory. Astronomers are used to puzzles. They thrive on them. But this particular puzzle had edges that didn't seem to align with any picture they recognized. The early universe was supposed to grow slowly. Gas clouds needed time to collapse. Stars required time to ignite. Galaxies needed epochs to gather themselves into coherent structures. And yet, here were objects that appeared to have skipped several intermediate steps, leaping directly into adulthood while the universe was still learning to walk. The unsettling part was not just their existence, it was their abundance. The deep fields weren't showing one extraordinarily massive outlier, but a population of them. If even a fraction of the early estimates held true, then something fundamental about galaxy formation needed reconsideration. Perhaps gas collapsed more efficiently in the early cosmos than models assumed. Perhaps star formation ignited in violent, accelerated bursts. Or perhaps mass estimates were being tricked by an unknown factor, something subtle, buried in the photometric signals, making these galaxies appear heavier than they truly were. But in that first wave of discovery, none of these explanations softened the emotional effect. There was a feeling, quiet but unmistakable, that cosmology had just cleared its throat, politely but firmly, a signal that the neat narrative of galaxy growth might require amendments. The researchers did what scientists must always do in such moments. They went back to the data. They reran redshift models with alternate assumptions. They checked the impact of emission lines on brightness. They combed through spectral energy distributions, pixel by pixel, measuring the faint signatures of distant starlight. They worked late hours in rooms lit by monitors and cold coffee, hoping to find the miscalculation that would return the universe to its expected behavior. But while refinements did later alter some mass estimates across the broader field, those first nights of analysis captured something more significant than any individual object. They marked a shift in how astronomers thought about the early cosmos, not as an empty stage waiting for structure, but as a place already bustling with activity, busy enough that some galaxies seemed to defy their assigned timelines. It wasn't a crisis. It wasn't evidence that cosmology had failed. It was a reminder that the universe is not obligated to obey human convenience. It follows paths determined by physics, not by predictions. Sometimes those paths are gentle and expected. Other times they sweep upward in ways that force researchers to revise assumptions, redraw boundaries, and rethink the tempo of cosmic growth. In the end, the significance of that night, and the nights that followed, was not that massive galaxies existed earlier than anticipated. It was the dawning awareness that the early universe might be more confident, more assertive, and more efficient than anyone had imagined. A place where light gathered quickly, where gravity worked with remarkable ambition, and where galaxies did not wait politely for the universe to reach maturity. They simply arrived, large, luminous, and ready to challenge every expectation placed upon them. Chapter 3. How a Galaxy Can Look Older Than the Universe. It lives in astronomy, light is both a messenger and a trickster. It carries stories across billions of years, whispering tales of creation and collapse, structure and silence. But it also disguises itself in ways that make even the most seasoned astronomer pause, squint, and wonder if the cosmos is gently teasing them again. Nowhere is this more apparent than in the early universe observations that first suggested the presence of galaxies that looked far too massive for their age, objects that seemed to have grown up faster than cosmic history permitted. At first glance, the brightness of a distant galaxy seems straightforward. Brighter means bigger. Bigger means more stars. And more stars mean a higher mass. But brightness is not always the honest witness it claims to be. Especially not when a telescope is peering across more than 13 billion years of cosmic expansion, decoding ancient photons that have been stretched, scattered, and transformed by every encounter along the way. One of the earliest clues that some of these suspiciously mature galaxies might be exaggerating their importance came from examining the influence of emission lines, those sharp, luminous fingerprints produced by excited atoms within star-forming regions. In a normal setting, these lines are a fascinating diagnostic tool, telling astronomers about gas composition and star-forming activity. But when a telescope measures light through broad filters, the way JWST often does for initial observations, these emission lines can masquerade as general brightness. A single powerful line slipping into a filter can make a galaxy appear far more luminous than its underlying continuum would suggest. Imagine a quiet conversation suddenly punctuated by someone shouting directly into a microphone. If you measured only the volume of the room, you might conclude that everyone inside was speaking loudly. Emission lines are that unexpected shout, an isolated flare mistaken for a sustained roar. Dust adds another layer of confusion. Cosmic dust, tiny grains of carbon, silicates, and other elements, softly reddens the light passing through it. In nearby galaxies, astronomers can usually distinguish dust effects with relative ease. But at extreme distances, where the universe itself has stretched light far into the infrared, redness becomes a slippery clue. A galaxy might look red because it is old and full of mature stars, or because dust is shading its light, or simply because cosmological redshift has dragged its photons across the spectrum. Distinguishing these possibilities from one another is like trying to determine the age of a distant mountain based solely on its silhouette in a fog. It is possible, but the potential for misjudgment is high. Then there is the subtle influence of active galactic nuclei, compact, energetic engines powered by accreting black holes. Even at early times, some galaxies contained these hidden furnaces. When an AGN is present, it pumps out radiation that can dominate a galaxy's brightness, lighting it up like a city with a power plant operating at full blast. To an observer measuring total luminosity, this can easily look like the glow of billions of stars. and even if the true stellar component is far smaller. These complexities aren't flaws in astronomical measurement. They are simply the consequences of studying a universe that rarely offers uncomplicated data. Light from extreme distances arrives altered, filtered by time, by space, by the expansion of the cosmos itself. Every number derived from that light carries layers of interpretation, each of which must be carefully peeled away. And at extreme redshift, the fragility of early mass estimates becomes even more pronounced. When only a few broad filters are available, astronomers have to build models based on sparse data points. Tiny uncertainties in the shape of a galaxy's spectrum can ripple outward into dramatic differences in inferred mass. A handful of misplaced photons can shift an estimate from small and energetic to massive and alarming. Early results were not wrong. They were simply provisional, the scientific equivalent of tracing a figure through frosted glass before seeing it clearly. This is where astronomy demonstrates one of its most admirable qualities: patience. The field moves slowly, not out of reluctance, but out of respect for how easily first impressions can mislead. When early observations suggested galaxies that appeared older than the universe they occupied, astronomers did not leap to write new physics into existence. Instead, they revisited assumptions, examined the fingerprints of emission lines, reevaluated dust contributions, and searched for the faint hints of AGN influence. Gradually, as follow-up observations accumulated and spectroscopy began offering more precise measurements, a more nuanced picture emerged. Some galaxies truly were brighter and more substantial than expected, demanding genuine revisions to models of early formation. Others, however, were simply bright in ways that did not translate neatly into mass. They were enthusiastic performers, not heavyweight champions. The difference between appearing massive and being massive is not a minor distinction. It reminds astronomers that even in a universe governed by strict physical laws, interpretation remains an art shaped by inference, calibration, and humility. Light tells its story, but it does not always speak plainly. In the end, the early wave of surprising brightness taught a gentle, necessary lesson that the universe reveals itself slowly and sometimes mischievously, that the most confident interpretations must still bow to new data, and that being wrong, quietly, gracefully, and amendably, is part of astronomy's long and steady dance with the cosmos. The galaxies that once seemed impossibly ancient did not vanish. They simply settled into clearer identities, and astronomy, wiser for the missteps, continued forward with the same careful wonder that has always guided it, listening closely, learning slowly, and embracing the vast patience required to understand a universe that seldom offers easy truths. Chapter 4. Spectroscopy enters the room and turns on the lights. In the earliest months of deep JWST analysis, the astronomy community found itself in a familiar but uncomfortable position, relying heavily on photometric redshifts, estimates of cosmic distance inferred from how much a galaxy's light is stretched across a few broad filters. Photometry is indispensable, elegant, and remarkably efficient. It can survey vast portions of the sky, flag distant candidates, and sketch a preliminary portrait of the universe's structure. But it also behaves a little like a courteous acquaintance, confident enough to offer hints, yet vague on the finer details. Photometry says, this galaxy seems very far away, with the same tone someone might use when saying, "Your cat seems hungry." It is a helpful suggestion, not a definitive diagnosis. Spectroscopy, on the other hand, is the friend who walks into the room, sits down with the data set, and begins checking receipts line by line. No assumptions, no interpretive leaps, just the raw patterned barcode of a galaxy's light, broken into thousands of tiny intervals, revealing its identity with unambiguous precision. When JWST began taking spectra of the earliest galaxy candidates, this shift felt almost ceremonial. After months of debating potential masses, distances, and the true nature of suspiciously bright objects, astronomers finally had access to the instrument designed to end arguments gracefully. Near-spec, the near-infrared spectrograph. In many ways, it played the role of a cosmic auditor, reviewing the claims photometry had filed and occasionally issuing quiet corrections. The difference between photometric and spectroscopic redshifts lies in how directly they touch the data. Photometric redshifts rely on the shape of a galaxy's overall spectrum as captured through broad filters. If certain wavelengths appear missing or dim, it suggests that the light has been shifted by cosmic expansion, placing the galaxy at great distance. But broad filters can blur features together, and strong emission lines can masquerade as continuum. Dust can distort color. Active nuclei can exaggerate brightness. A galaxy's entire identity can shift based on how a handful of data points align, like judging a book by the shade of its cover rather than by reading its pages. Spectroscopy, in contrast, reads those pages slowly and thoroughly. It identifies exact wavelengths of light corresponding to hydrogen, oxygen, and other atomic signatures. Because these lines shift with cosmic expansion, they offer a precise measurement of redshift, one that cannot be faked by dust, emission lines, or enthusiasm. When the first spectroscopic confirmations began arriving, the tone across research teams changed. It was subtle at first, a quiet blessing from the data itself. Some galaxies that photometry had suggested were astonishingly distant turned out to be somewhat nearer. Not ordinary, but not epoch-shattering either. Their colors had been misleading, their brightness influenced by emission lines, their photometric estimates optimistic. These galaxies weren't frauds. They were simply misunderstood. Others, however, held their ground beautifully. Their spectra revealed unmistakable signatures of extreme distance. The telltale drop-offs in hydrogen absorption, the delicate slopes carved by cosmic expansion, the crisp spectral lines marching across detectors in silent confirmation. These were the galaxies that truly rewrote timelines, the ones that future textbooks will mention with a kind of reverent understatement. But the process of disentangling candidates from confirmations brought an important lesson into sharp focus. Early universe astronomy cannot rely on photometry alone, not because photometry is flawed, but because the cosmos is too complex for any single method to hold all the answers. Light travels across billions of years, gathering distortions like souvenirs. By the time it reaches a telescope, it needs careful translation. Photometry offers the broad strokes. Spectroscopy offers the detail work. An IR spec became, in those first months, the instrument everyone waited for with equal parts excitement and trepidation. It had the quiet power to validate the most extraordinary claims or gently deflate them. Some researchers joke that sending a galaxy candidate through NIR spec was like submitting a manuscript to a very strict reviewer, one who returned results not with commentary but with immutable numbers. As more spectra accumulated, a pattern emerged. The earliest galaxies were indeed brighter and more abundant than models predicted, but not always in the extreme ways initial analyses suggested. Some early headlines declared that cosmology was broken, but spectroscopy softened these claims into something more thoughtful and much more scientifically satisfying. The universe had not been caught violating its own rules. It had simply been misunderstood through the haze of limited data. Spectroscopy revealed a cosmos that was busy, efficient, and vibrant, but not chaotic. It clarified distinctions between galaxies, shaped by intense star formation, objects brightened by emission lines, and sources energized by compact nuclei. It helped refine the timeline of cosmic dawn without discarding the foundations of cosmic history. In many ways, the arrival of NIR Spec's first results felt like someone turning on the lights in a dim room. Shapes that once appeared exaggerated or ambiguous settled into clarity. Distances that seemed improbable resolved into measured truths. The early universe, illuminated line by line, became less a source of confusion and more a source of wonder at its subtle complexity. And as astronomers continued to sift through thousands of spectra, a new rhythm formed, one in which photometry and spectroscopy worked hand in hand. Photometry, polite and broad in gesture, pointed to where the mysteries lived. Spectroscopy followed behind with quiet authority, translating hints into knowledge and ensuring that every extraordinary claim stood on the bedrock of measured light. In the end, the story of those early months was not about contradictions or corrections. It was about the precision required to understand a universe that speaks softly and in code. A universe that offers its secrets willingly, but only to those patient enough to read them one wavelength at a time. Chapter 5. The Record Breakers That Actually Held Up. Every so often in astronomy, a discovery arrives that doesn't rush to announce itself. It simply appears, steady, unwavering, confident in its own existence, while the scientific community gathers around it with hesitant excitement. That was the mood when researchers first glimpsed the faint, distant glow of the galaxy now known as JWST 14-0. It entered the scene without spectacle, a soft smudge in deep JWST imaging, the kind of object astronomers might normally note briefly before moving on. But this one did not behave like a routine distant galaxy. It lingered. It persisted through every test, every refinement, every attempt to demote it to something more ordinary. And slowly, it became clear that this small patch of ancient light was going to hold its ground at a place in cosmic history where galaxies were barely supposed to exist at all. When its spectroscopic redshift came back as Z equals 14.32, the room, for once, fell quiet. This number, deceptively simple, meant that the galaxy's light began its journey less than 300 million years after the Big Bang. To put that into perspective, imagine the universe as a lifelong companion whose history spans a full calendar year. By this analogy, the light from Jade's JWST 14-0 would have set out sometime during the first hour of January 1st, when cosmic time was still raw and forming its earliest patterns. Most galaxies we know and admire, spirals, ellipticals, all the grand structures, wouldn't appear until much later in this metaphorical year, often not until summer or autumn. Yet, Here was a galaxy living in the cosmic equivalent of dawn's earliest glow, already luminous enough to be seen across billions of years. Its physical characteristics only deepened the astonishment. At roughly 1,700 light-years across, it is small compared to galaxies of later epochs, but remarkably well-formed for its age. It was not merely shining faintly in the background. It was actively producing stars at a rate of about 20 per year, a pace that suggested a confident, energetic engine at its core. The universe, at this early time, seemed to be moving more quickly than anyone had predicted. But perhaps the most striking aspect of its discovery was not the scale or the brightness, or even the star-forming vigor. It was the conformation. In astronomy, distance records mean little without firm verification. Photometric hints are like rumors whispered through cosmic static, enticing but uncertain. Spectroscopy, however, is the final word, and this galaxy's spectral signature left no ambiguity. It belonged to an era when cosmic structures were expected to be fragile and rare, yet it stood there, sturdy and illuminating as though it had always belonged. Plug quietly, without demanding attention, JADES-GS-Z14-0 rewrote the timeline of early galaxy formation, not through dramatic contradiction, but through the gentle, unavoidable reality of measured light. There was no triumphal announcement, no proclamation that the universe had betrayed expectations. Instead, the reaction across the community was one of subdued awe, a kind of reverent recognition that the cosmos continues to exceed our sense of pacing. Observers spoke of the discovery with a tone reminiscent of meeting someone unexpectedly wise at a remarkably young age. Not disbelief, but respect. This galaxy did not force theories to collapse. It nudged them, politely but firmly, toward new territory. Its existence suggested that star formation could proceed efficiently far earlier than models had assumed, that matter could gather into coherent structures more rapidly, that the conditions of the early cosmos were not as slow or hesitant as once imagined. And yet, it also offered reassurance. The universe was not chaotic. It was simply more capable than predicted. The same physics still governed starbirth, gas collapse, and gravitational clustering. What changed was our understanding of how swiftly these processes could take place under the intense densities and temperatures of the universe's first few 100 million years. In its stillness, JADES-GS-Z14-0 became an anchor, something fixed and undeniable in a sea of early uncertainties. Headlines could come and go, debates could rise and settle, but the galaxy's spectrum remained firm. It was there, shining faithfully from a chapter of cosmic history we had barely begun to read. The more astronomers studied it, the more its presence shaped new questions rather than ending old ones. How common were galaxies like it? Was this an extraordinary outlier or part of a broader population emerging with JWST's sensitivity? If one galaxy could form this early, perhaps dozens or hundreds had as well, waiting in the faint edges of deep fields. What made the discovery remarkable was not that it set a record — astronomy records fall often and quietly — but that it held the record under scrutiny. It endured the rigorous process of analysis, the skepticism that surrounds any extraordinary claim, and the delicate corrections that typically erode initial excitement. But nothing eroded. The galaxy's identity only sharpened. And in that sharpening came a sense of gratitude, an acknowledgement that the universe still has the capacity to surprise without overwhelming, to challenge without undermining, to illuminate without blinding. JADES-GS-Z14-0 is not a loud discovery. It does not shout its significance. It simply shines softly and persistently from a moment when the cosmos was young beyond comprehension. A reminder that even at the very beginning, the universe was already busy becoming itself. Chapter 6. When the early universe turned the lights on. Too soon. In the earliest era of cosmic history, long before galaxies settled into familiar shapes or stars shimmered with steady brilliance, the universe was wrapped in a dense, opaque fog of neutral hydrogen. It filled every corner of space like a heavy morning mist that refused to lift. This was a time often described as the cosmic dark ages, not because nothing existed, but because even the brightest young stars couldn't easily pierce the haze surrounding them. Light traveled only with difficulty, scattered by atoms that absorbed and re-emitted it until its original shape was nearly lost. In this landscape, illumination came slowly. The first generations of stars burned fiercely, but their light had to carve tunnels through the surrounding gas, creating small cavities of clarity, tiny lantern-lit spaces in an otherwise dim expanse. Over time, as more stars ignited and more galaxies took shape, these patches grew and merged. Eventually, the universe transitioned from opaque to transparent in a grand process known as reionization, a milestone that marked the moment when light finally traveled freely through vast distances. Models long suggested that this transformation should unfold gradually, becoming truly effective only several 100 million years after the Big Bang. The early cosmos was not expected to rush. It was a massive structure learning to organize itself, gathering materials, forming stars cautiously. The idea that large, powerful galaxies could ionize their surroundings early in this era felt optimistic, almost indulgent. Then came JWST 13.1, a deceptively small patch of light sitting at Z equals 13.05, quietly unsupervised in the deep JWST data. At first, it looked like yet another distant candidate. Interesting, yes, but not necessarily revolutionary. Many galaxies at extreme redshift share the same faint reddish glow. But when its spectrum was analyzed, an unexpected signal leaped from the data, a clear Lyman alpha emission line. This particular line is the universe's equivalent of a delicate, easily snuffed out flame. Lyman alpha photons interact strongly with neutral hydrogen, and the early universe was drenched in that very hydrogen. Any Lyman alpha light trying to escape should have been absorbed almost instantly, leaving no trace by the time it reached us. The detection of this line at such extreme distance meant something unusual was happening around this galaxy, something that required rewriting the quiet assumptions of early cosmic structure formation. The most straightforward explanation was also the most astonishing. This galaxy must have created a bubble of ionized gas around itself, a clear pocket in the fog, vast enough for Lyman alpha photons to slip through and escape. In simpler terms, the universe had not yet finished building its walls. But someone had flipped the light switch anyway. This lone, ancient galaxy was illuminating more than its surroundings. It was challenging the timeline of reionization itself. If it could carve out a transparent bubble in an epoch still thought to be saturated with neutral hydrogen, then either galaxies formed earlier than expected, produced ionizing radiation more efficiently or clustered in ways that intensified their combined influence on surrounding gas. None of these possibilities was trivial. Each one hinted at a universe far more industrious and coordinated in its earliest stages than earlier models assumed. The presence of Lyman Alpha also suggested that this wasn't a sheltered galaxy hiding quietly in a cosmic corner. It was active, energetic, and surrounded by conditions that favored the rapid transformation of gas. Somehow, it had created enough ionizing photons to punch a hole in the surrounding medium, something only a vigorous population of hot young stars or a powerful central engine could accomplish. Whether through sustained star formation or some more concentrated burst of activity, the result was the same: a transparent path through a time that should have remained opaque. As more researchers examined the data, the implications deepened. If JWST 13.1 had formed an ionized bubble, it was unlikely to be alone. Galaxies do not evolve in isolation. They grow in loose communities shaped by gravity and shared resources. A group of early galaxies, igniting around the same time, could carve out shared cavities of ionized gas, even before reionization became a global phenomenon. This changed the tone of early universe research. Instead of imagining reionization as a smooth, uniform brightening, like a slow sunrise washing across a still landscape, the new picture resembled something more uneven, almost patchwork. Ionized regions forming here and there, irregular and scattered, gradually expanding until they overlapped like candle flames merging in the dark. What had been assumed to be a gradual dawn now looked more like a field of early sparks, flickering unpredictably. For astronomers working on models of cosmic evolution, this was both thrilling and inconvenient. Thrilling because it meant the early universe was more dynamic than previously understood. Inconvenient because it required the careful untangling of old assumptions, followed by new simulations, new parameters, and a renewed appreciation for how easily a single line in a spectrum can nudge an entire field forward. And yet, despite its significance, the discovery did not inspire declarations of overturned theories or broken cosmology. Instead, it invited a sort of respectful awe, a sense that the universe once again had gently extended a hand and revealed something beautiful, something subtle that had been there all along, waiting for a telescope sensitive enough to notice. In the glow of JWST 13.1's escaped Lyman alpha photons, one can almost picture the early cosmos as a vast construction site, half-finished walls rising through fog, while galaxies moved about with lanterns, illuminating small pockets long before the structure was complete. It was messy, premature, and profoundly human in its improvisation. The universe wasn't supposed to turn the lights on yet, but it did, and that quiet defiance continues to guide our understanding of cosmic dawn, one unexpected photon at a time. Chapter 7. The Swiss Cheese Universe. When cosmologists first began imagining the universe's transition from darkness into light, the image that tended to appear in textbooks and public descriptions was one of gentle inevitability. A soft glow rising across the cosmos as the first stars flickered awake, a gradual brightening that washed away the neutral hydrogen fog in a smooth, orderly wave. It was an appealing metaphor. Cosmic dawn as a sunrise, slow and symmetrical. But the more deeply astronomers examine the earliest stages of reionization, the clearer it becomes that the universe did not move gracefully from shadow to clarity. Instead, it behaved more like someone poking uneven holes in a curtain, light leaking through patch by patch in unpredictable shapes and locations. This is the era now being re-envisioned as a Swiss cheese universe, full of bubbles and gaps, where ionized pockets formed and expanded in an irregular mosaic rather than a uniform glow. The heart of this patchiness is straightforward. Early galaxies did not cooperate with one another. They ignited at different times, with different intensities, and inside regions of space that varied wildly in density. Some galaxies radiated enough high-energy photons to carve out enormous cavities in the surrounding hydrogen, effectively clearing a transparent sphere around themselves. Others barely managed to create a thin clearing before being overwhelmed by the fog. Because of this uneven activity, reionization wasn't a synchronized event. It was a collection of local revolutions, each galaxy fighting its own battle against the darkness. Where many of them clustered together, combining their output, larger bubbles formed more quickly. In quieter regions of space, the fog lingered, untouched and opaque. The cosmic landscape became a patchwork quilt stitched together by scattered glowing pioneers. This understanding offers insight into the tempo of early structure formation. Dense regions where gravity gathered matter efficiently produced stars at a furious pace. Those stars generated intense ultraviolet radiation, which in turn forged ionized islands in the fog. Over time, these islands expanded and overlapped, merging into vast networks that gradually punctured the neutral background. But the process was uneven, what with edges that twisted and curled like ink spreading through water. Older models portrayed reionization as a universal softening, a serene progression where the opacity faded gently, almost ceremonially, as though the universe were dimming lights in an old theater. Yet modern observations paint a far more dynamic picture. Instead of a sweeping front of clarity, reionization resembled thousands of scattered lanterns, each pushing back the darkness in its own irregular shape. The implications of this roughness are profound. If ionized regions formed early and aggressively around certain galaxies, it suggests that star formation was highly efficient in localized pockets. Gas collapsed rapidly, stars ignited in tight bursts, and radiation surged outward with surprising strength. Even small galaxies may have contributed to this process, while acting as persistent sparks rather than brief flashes. These bubbles also reveal something about the cosmic terrain in which they formed. Regions of higher matter density were fertile grounds for early activity. Gravity gathered material more quickly, stars condensed sooner, and ionization spread outward like a brush fire. Meanwhile, vast stretches of the cosmos, less dense and slower to form stars, remained untouched for longer periods. This unevenness reshapes the narrative of the early universe from one of symmetry to one of contrast. The Swiss cheese model captures this beautifully. Instead of imagining reionization as a single continuous transformation, it becomes a dynamic interplay between illumination and resistance. Light punched through openings while neutral hydrogen filled the gaps, while clinging to whatever space had not yet been claimed. The universe looked less like a brightening horizon and more like a wall full of glowing apertures. And the boundaries of these cavities were not neat. They rippled and wavered, shaped by the interplay between radiating sources and their environments. The edges were fuzzy, transitional zones where light continually strained against the encroaching fog. As these regions expanded, they sometimes collided with neighboring bubbles, combining into larger territories of transparency. Other times, they stalled, blocked by dense pockets of gas that refused to yield. This uneven illumination has consequences that reach far beyond the aesthetic. It affects how galaxies interacted with their surroundings, how matter cooled and collapsed, and how the earliest cosmic structures evolved. In a patchy universe, galaxies near the borders of ionized regions experienced very different environments from those deep within clear pockets. Some sat immersed in bright ionized surroundings, while others remained shrouded in neutral hydrogen, conditions that influenced their growth, their star formation, and even the radiation that reached them from nearby sources. The revised view of reionization also alters how cosmologists interpret distant signals. A galaxy's light, passing through a partially ionized region, might retain certain spectral features, while another galaxy, even at a similar distance, might have its signature entirely obscured by the fog. The unevenness complicates observations, but it also enriches them, offering clues about the shape, size, and distribution of ionized bubbles across the early cosmos. Perhaps the most humbling aspect of this revised picture is how unscripted it feels. Cosmic dawn was never a single event. It was a disordered, overlapping sequence of local transformations, each driven by the unpredictable emergence of stars and the uneven clustering of matter. The universe did not wait for a coordinated moment to become transparent. It simply brightened wherever it could, whenever a galaxy was bold enough to push back against the fog. If the ceremonial metaphor once dominated, Rionization is a silent sunrise, the Swiss cheese version replaces it with something more organic, more chaotic, more honest. Light did not rise evenly. It seeped, burst, pooled, and wandered. It flickered through gaps and carved tunnels. It behaved like something discovering itself for the first time. And in that messy illumination, we find a universe not defined by order, but by improvisation, its earliest chapters written in uneven strokes of brilliance long before equilibrium arrived. Chapter 8, Black Holes, that showed up uninvited. In the deepest stretches of cosmic time, when the universe was still young enough to be measured in mere hundreds of millions of years, astronomers expected to find small galaxies tentatively gathering their first stars. What they did not expect to find were galaxies already hosting ravenous black holes, compact, energetic engines behaving as though they had skipped several prerequisite chapters of cosmic development. Yet there they were, unmistakably present, lighting up regions of space that should have been far too early for such dramatic behavior. One of the clearest examples lies within the compact, unassuming structure of GN-11. It's a galaxy already famous for residing in a strikingly early chapter of cosmic history. Its age, less than 500 million years after the Big Bang, places it at a time when galaxies were expected to be cautious, dim, and structurally fragile. But when JWST's spectroscopic instruments examined this tiny cosmic inhabitant, something far less delicate emerged from the data. The spectrum contained features that no simple young stellar population could explain. Instead, it displayed the unmistakable markers of dense, highly ionized gas so thoroughly energized that only an intense, compact, and persistent radiation source could produce it. High ionization emission lines appeared like glowing signposts in the data, each one hinting that the galaxy was not merely forming stars, but harboring something more assertive, an actively accreting black hole. Accretion, the steady infall of matter onto a black hole, is one of the brightest processes in the universe. Paradoxically, the object doing the consuming remains invisible. It is the swirling, heated, tortured material spiraling into oblivion that shines. In GNZ11's case, the spectral clues suggested that this radiation was not a gentle flicker, but a sustained blaze, intense enough to dominate some of the galaxy's output, a beacon from an era when beacons were not expected at all. Finding an accreting black hole at this epoch is a bit like walking into a newly constructed house and discovering someone has already installed a high-powered industrial furnace in the living room. Before the paint dries, before the plumbing is finished, before the furniture arrives, there it is, roaring contentedly, radiating more energy than anything else in the building. Galaxies of this age aren't supposed to have such features. They aren't even supposed to have the cosmic equivalent of walls strong enough to hold them. And yet, GNZ11 not only hosted one, it hosted one with enough influence to reshape the galaxy's entire environment. The presence of such a black hole also carries implications for early galaxy brightness, one of the most persistent puzzles of the JWST era. When a galaxy shines unusually brightly at a time when mass should still be accumulating, astronomers naturally ask, what is powering that luminosity? Star formation can generate substantial light, particularly if it occurs in intense bursts. But there are limits. A compact, accreting black hole, however, can easily boost a galaxy's apparent brightness, especially in the ultraviolet and near-infrared bands. It effectively cheats the cosmic timeline by making the galaxy appear older, larger, or more energetic than its actual stellar population warrants. This matters because brightness influences everything astronomers infer about a distant galaxy: its mass, its star formation rate, even its potential role in reionization. If black holes were active this early, they may have contributed more significantly to the ionizing photon budget than previously believed. The early universe might have been shaped not only by young stars and turbulent gas, but also by compact engines flaring in the hearts of galaxies barely old enough to form stable structures. The spectral signs of dense gas surrounding GNZ11 add another intriguing layer. Such gas doesn't simply appear, it requires an environment capable of sustaining rapid infall and intense heating. This suggests that the galaxy was not a fragile assembly of primordial material, but a surprisingly organized system, dense enough to feed a central black hole, yet chaotic enough to support rapid star formation around it. The coexistence of these processes hints at an early universe that wasted no time experimenting with complexity. These discoveries open the door to deeper questions about how black holes originated. Were they born large through direct collapse, forming from massive gas clouds that skipped the intermediate steps? Did they grow at astonishing speeds in dense environments, fed by ample reservoirs of primordial material? Or did some combination of early conditions make it easier for them to thrive before galaxies even found their footing? Whatever the mechanism, the outcome is unmistakable. Some galaxies hosted black holes before they had time to decorate, settle in, or establish anything resembling cosmic stability. These galaxies were barely newborns, yet they carried engines usually associated with much later stages of evolution. It is as though the universe allowed them to borrow technology from a future era, using it enthusiastically while the rest of cosmic structure was still learning basic assembly. The presence of these early black holes doesn't disrupt cosmology. It deepens it. It reveals that the early universe was capable of supporting gravitational extremes far earlier than models once suggested. It underscores how quickly matter can organize itself under the right conditions. And perhaps, most strikingly, it shows that light in this era came not only from stars tentatively illuminating their surroundings, but also from compact objects burning with intense focused energy. In the quiet glow of GNZ 11's spectral signature, one sees a universe that did not wait for permission or stability before beginning its most dramatic work. Black holes, uninvited but undeniably present, stepped into the cosmic stage early, reshaping galaxies, influencing brightness, and adding complexity long before the universe had settled into a predictable rhythm. They were not supposed to be there yet, but they arrived anyway, radiating with the confident disregard of guests who show up early, make themselves comfortable, and begin changing the atmosphere long before anyone else walks through the door. Chapter 9. The Heavy Seed Problem. In the long ledger of cosmic puzzles, few have been as quietly persistent as the question of how massive black holes appeared so early in the universe. By the time the cosmos reached its first few 100 million years, a fragile, formative era, astronomers began detecting quasars with black holes weighing hundreds of millions, even billions of solar masses. These giants were not subtle. Their brilliance lit up enormous distances, announcing their presence with a confidence that felt suspiciously premature. The problem is simple to state, but difficult to solve. There just wasn't much time for them to grow. Under ordinary astrophysical conditions, black holes grow by accreting gas or merging with other black holes. But these processes take time, immense stretches of it. Even if early black holes consumed matter at the theoretical maximum rate, their growth remains limited by radiation pressure, which pushes material away as the black hole becomes too luminous. The result is a natural throttle, an upper limit to how fast they can gain mass. It's an elegant mechanism, but one that makes it especially hard to produce billion solar mass objects in the early universe. And yet, there they were, bright, heavy, and unquestionably present. This conundrum led astronomers to consider whether some black holes were born large, rather than starting from the tiny remnants of early stars. Instead of growing from light seeds, the few solar mass leftovers of supernova explosions, perhaps some began life as heavy seeds, already weighing tens of thousands or even hundreds of thousands of suns. This is where the idea of direct collapse black holes emerges. In these scenarios, instead of forming stars that eventually explode, enormous primordial gas clouds might have collapsed directly under their own gravity, bypassing the stellar phase entirely. These collapses would produce black holes with much larger starting masses, cosmic infants that arrived already tall for their age. The physics behind this possibility is subtle. For a direct collapse event to occur, the gas cloud must avoid fragmenting into smaller clumps that would otherwise form stars. Fragmentation is the default behavior of cooling gas, so something must prevent it. Perhaps strong radiation fields from nearby galaxies, or conditions so hot and dense that star formation becomes inefficient. In these rare environments, the gas cloud could collapse as a single, massive entity, forming a black hole with the gravitational presence needed to grow into a giant on a cosmic deadline. The idea remained mostly theoretical for years, a compelling possibility, but one lacking the observational detail needed to ground it. That began to change as JWST gathered its earliest deep field spectra. Among the surprising detections were signs of exceptionally luminous, compact sources around Z, approximately 10. Not yet quasars in the traditional sense, but objects whose emission suggested intense activity around a central black hole. One such example, captured in a lensed galaxy at extreme distance, showed X-ray and mid-infrared signatures consistent with a black hole that was already too massive for a typical stellar remnant seed at that epoch. Even allowing for rapid accretion, the timing simply didn't add up unless the black hole had begun life with a substantial head start. The environment around it, dense, turbulent, and still gathering structure, provided a natural arena for accelerated growth, but even that could not fully explain its mass without invoking an unusually large seed. These observations do not prove the direct collapse scenario, but they strengthen the case that something unconventional occurred in the early universe. This is not a claim of exotic physics or an overhaul of gravitational theory. It is simply an acknowledgement that the universe may have chosen a more efficient route for building some of its earliest compact objects. The heavy seed idea also reframes how astronomers view early galaxy evolution. That if some galaxies hosted massive black holes almost from birth, their internal dynamics would have been shaped by these central engines. The radiation from early accretion could heat surrounding gas, influencing star formation. It could drive small outflows, clearing cavities or stirring turbulence in ways that echo through the galaxy's development. Black holes would not merely be byproducts of galactic evolution. They would be active participants from the start. Yet the presence of heavy seeds does not imply that all early black holes formed this way. The universe likely produced a diversity of seeds, each shaped by local conditions, some born from massive stars, others from collapsing gas clouds, and still others forged through mergers of smaller black holes. This mixture helps explain the wide range of black hole masses inferred at early times. It also tempers the desire for a single, sweeping explanation. The early universe was rarely uniform. Its processes were as varied as the environments from which they emerged. The elegance of the heavy seed hypothesis lies in its modesty. It does not reshape cosmic history. It fills in gaps where growth rates alone struggle to keep pace with observations. It proposes no contradiction, only refinement. There is no claim that every early supermassive black hole began as a heavy seed, only that some likely did, paving the way for the luminous quasars we now detect at redshifts once thought unreachable. In the quiet space between theory and observation, this idea offers a grounded, patient understanding of cosmic complexity. The early universe was not in a hurry, but it was efficient. Given dense gas, intense radiation fields, and the gravitational pull of assembling structures, it may have found ways to build large black holes faster than the more familiar pathways allow. The heavy seed problem, then, is not a crisis, but a clue, a signpost pointing toward the remarkable ingenuity of cosmic evolution. It reminds us that the universe is capable of surprising solutions born not from breaking laws, but from fully exploiting the ones already in place. And in that steady, unhurried realization, astronomers find a deep comfort. The universe does not need to bend the rules to astonish. It only needs to play them with subtlety. Chapter 10. The Quiet Invasion of the Little Red Dots. Astronomy is no stranger to unexpected guests. The universe has a long history of presenting phenomena no one asked for, wrapped in faint glimmers of mystery and deposited gently into the data. But even by cosmic standards, the appearance of the little red dots was unusually abrupt. They were not predicted. They were not requested. They were simply there, in surprising numbers, scattered across deep field images like cosmic punctuation marks that refused to be ignored. The name itself, Little Red Dots, perfectly captures the scientific community's initial reaction, a mixture of bemusement, understatement, and the quiet resignation that this would soon become someone's dissertation topic. It is a label conceived in the moment before understanding, when something is too distinct to overlook yet too enigmatic to categorize. Not galaxies, not stars, not quasars, at least not in the traditional sense, just dots, red ones, and quite a lot of them. Their defining traits were deceptively simple. They were very compact, often appearing as unresolved or barely resolved spots. They were intensely red, far redder than expected for their sizes. They were abundant, showing up in surveys where only a handful had been anticipated. The first hints came from the CEERS survey, one of JWST's early wide-field imaging campaigns. Researchers scrolling through the images noticed tiny crimson flecks that defied expectations. A few such dots could have been ignored, attributed to peculiarities or noise. But they kept showing up. Then more appeared in the JADES data. And then, as if determined to remove any doubt about their existence, an even larger population emerged in the Cosmos Webb observations, hundreds and hundreds of them scattered across half a square degree of sky. Like quiet guests drifting into a gathering without announcement or invitation, they arrived with neither explanation nor apology. Their abundance was immediately perplexing. Nothing in earlier models suggested that the early universe should produce a population of compact red objects in such quantities. They were too numerous to be rare outliers and too consistent in appearance to be coincidental. Something, perhaps several things, was shaping them into a coherent population. But what exactly were they? Their extreme redness was the first major clue. Red light can imply great age, significant dust, or extreme distance. Yet the sizes of these objects suggested a mismatch. If they were ancient, they were far too small. If they were dusty, they were unusually compact for such obscuration. And if they were incredibly distant, well, then their brightness and colors weren't quite lining up with expectations either. It was as though each explanation fit part of the puzzle but left other pieces awkwardly dangling. This ambiguity contributed to the sense that astronomers had stumbled onto a category the universe had named before anyone could classify it. The phrase little red dots became both a placeholder and a reluctant admission. We see them, we recognize them, but we do not yet know what they are. The ease with which JWST detected them also shifted the tone of early universe research. These objects were not faint, hidden in the data's margins. They were bold enough to stand out even in quick-look images. Their compact shapes made them resemble cosmic embers, glowing persistently from an era when many galaxies were still forging their first brilliant bursts of starlight. The more researchers cataloged them, the more their significance grew. Hundreds of candidates spread across disparate surveys suggested a population-level phenomenon, not a handful of exotic anomalies. It wasn't one peculiar dot. It was a quiet invasion of them. Their presence invited numerous theories, each compelling in its own right. Perhaps they were extremely young galaxies undergoing intense star formation, their redness caused by emerging dust. Or maybe they were compact starburst regions, pockets of brilliant activity hidden behind newly formed clouds. Some evidence hinted at more energetic possibilities, that many little red dots might harbor accreting black holes, as making them miniature engines of radiation concealed within tight envelopes of gas. But these interpretations, however exciting, belong to later chapters of the unfolding narrative. In their earliest days, before spectra had been gathered or models refined, the little red dots were simply a surprise, a quiet one, but unmistakable. There is something subtly charming about their introduction to cosmic history. While other discoveries arrived with dramatic features or headline-grabbing luminosity, the little red dots appeared with a kind of cosmic modesty. They did not blaze like quasars or sprawl like galaxies. They did not distort space with gravitational lensing or reveal themselves through dramatic variability. They just nestled into the images, small and red and inexplicably numerous, patiently awaiting attention. Yet their discovery also demonstrated one of the enduring truths of astronomy. Progress is as often driven by unexpected abundance as by remarkable singularity. A single anomalous object can be dismissed as an outlier. 100 suggest a pattern. Hundreds more, appearing across multiple surveys, demand explanation. The little red dots were not a headline in the traditional sense. They did not shock the field with impossible properties. Instead, they whispered a question across deep field data. What is happening in the early universe that allows so many compact crimson objects to form? And in that whisper lay the seed of one of JWST's most intriguing new mysteries. They represent not a contradiction, but an invitation, an opportunity to understand the richness and complexity of cosmic evolution in a regime previously blurred by technological limits. The universe did not give them a dramatic name or an obvious category. It simply left them scattered across the sky like unclaimed clues from a story we are only beginning to read. Quiet, red, compact, and persistent, they arrived unannounced, and astronomers are still learning how to welcome them. Chapter 11, are the little red dots galaxies, black holes, or both? As astronomers began studying the little red dots more closely, those compact crimson sparks scattered across deep JWST fields, one thing became immediately clear. Their simplicity was an illusion. Behind their neat, round appearances lay a tangle of physical processes that refused to fit neatly into any familiar cosmic category. And these objects acted like galaxies on some days, like black holes on others, and occasionally like something that hadn't yet been formally introduced to astronomy. The first major clue that the little red dots might be more than just tiny red galaxies came from their spectra, the fingerprints of light that reveal what is truly happening inside an object. When several of these sources were targeted for spectroscopic follow-up, a striking signature appeared. Broad emission lines, features spread over wide ranges of wavelength, created when gas moves at extraordinary speeds near a powerful central source. These broad lines are the calling card of active galactic nuclei, or AGN, regions where matter swirls into a black hole, heating to temperatures so intense that it radiates in fierce luminous arcs. Gas caught in these gravitational whirlwinds travels at velocities of thousands of kilometers per second, stretching the spectral lines as surely as a potter stretching clay. When astronomers see broad lines, they know a black hole is nearby, eating, glowing, and shaping the environment. So, were the little red dots simply early AGN? At first, this possibility seemed elegant. Their compactness, their brightness, their deep coloration. These traits could easily result from a black hole wrapped in dense gas. Their abundance could hint at a surprisingly active early universe, where black holes formed and fed with remarkable efficiency. JWST's sensitivity might simply be revealing a previously hidden population of fledgling galactic nuclei. But elegance in astronomy often dissolves upon inspection, and this explanation ran into complications. Not every little red dot shows the clear hallmarks of AGN activity. Some display only faint or ambiguous line broadening. Others have colors that suggest dusty star formation rather than a central black hole. Dust, when warmed by intense starbirth, can redden the light of a galaxy dramatically, enough to mimic the hues of an AGN-dominated source. And some of the dots exhibit photometric slopes more consistent with stellar populations enshrouded in thick, newly formed dust clouds. This alternate interpretation introduces a different flavor of mystery. If the dots are dusty star-forming galaxies, they must be forming stars in unusually compact regions. Their scale suggests structures only a few hundred light-years across, far smaller than typical starburst galaxies. Yet their brightness implies that thousands of stars might be forming in these confined volumes, producing so much heat and radiation that the surrounding dust glows brightly in the infrared. Such behavior would place them among the universe's earliest and most efficient star factories, tiny cocoons bursting with newborn stars, hidden behind curtains of dust. This scenario is tantalizing, but it also stretches conventional understanding. Starburst regions tend to expand, disperse, and interact with their surroundings. The little red dots seem stubbornly compact, as though something is restricting their growth. The contradictions pile up. If they are AGN, why do so many lack strong X-ray signatures? If they are starbursts, why are their spectral features sometimes dominated by broad lines? If they are both, as some researchers suspect, how do these energetic processes fit together in such small packages? This identity crisis has become one of the early universe's quiet intrigues, the possibility that the little red dots represent mixed-mode objects where dusty star formation and early black hole feeding coexist in close quarters. In this hybrid scenario, the dense environments that fuel rapid starbirth might also channel gas toward a central black hole, igniting accretion and producing the broad lines observed in some spectra. The two processes, star formation and black hole growth, may be entangled rather than separate, each shaping the other. Yet even this interpretation has gaps. The physical pathways that produce such compact, dual-purpose structures are not fully understood, or simulations offer hints. Dense gas clouds collapsing under intense radiation turbulent flows feeding central cores, but they cannot yet reproduce the sheer abundance of little red dots detected by JWST. The dots seem too numerous, too consistently compact, and too uniformly red to fit comfortably into any existing category. Their behavior resembles a cosmic shrug, a phenomenon that insists on existing even though the universe's rulebook doesn't yet have a page for it. The identity crisis also reshapes the broader narrative of the early cosmos. If these objects are AGN-dominated, then black holes were more widespread and influential earlier than expected. If they are dusty starbursts, then the star formation was far more vigorous in confined spaces. And if they are hybrids, then the earliest galaxies grew through mechanisms more intertwined and chaotic than previously modeled. Each possibility nudges cosmological understanding in a different direction, yet none requires rewriting the laws of physics. Instead, the little red dots highlight something subtler. The early universe was capable of producing structures that sit in overlapping categories, resisting the neat taxonomies built from lower redshift experience. They remind astronomers that classification is a human tool, not a cosmic obligation. Their mystery persists, not because the data are poor, but because the data are richer than the frameworks built to interpret them. Observations sharpen their outlines while deepening the puzzle within. The dots keep their secrets with patience, offering clues only in fragments. A broadened line here, a dusty glow there, an abundance that defies assumptions. In their enigmatic glow, they reveal something essential about cosmic dawn. Complexity arrived early. The universe did not wait for maturity to experiment with starbursts, black holes, or their intimate coexistence. It built compact powerhouses that blended roles, challenging observers not with contradictions, but with possibilities. The little red dots may turn out to be galaxies, black holes, or both. But for now, they remain what they first appeared to be: small, red, quietly defiant, and undeniably real, insisting on their place in the cosmic story even before we fully understand the language they speak. Chapter 12. When simulations catch up to observations. When the first wave of JWST results spread through the astronomical community, the reaction oscillated somewhere between exhilaration and unease. The telescope was revealing galaxies earlier, brighter, and seemingly more mature than theory had comfortably predicted. Simulations, developed over years using careful assumptions about star formation, gas cooling, dark matter clustering, and cosmic expansion, suddenly looked as though they had been caught unprepared, like students confidently solving a practice exam only to find the real test written in a different dialect. But theory did not collapse. It blinked, adjusted its glasses, and began the steady work of catching up. Contrary to the breathless headlines that circulated at the time, cosmology was never in danger of breaking. The early universe was always a place of extremes, high densities, rapid cooling, and energetic interactions. What surprised researchers was the specific arrangement of those extremes, the abundance of compact galaxies, the brightness of distant sources, and the unexpected presence of exotic populations like the little red dots didn't violate physical laws. They simply stretched earlier assumptions about how efficiently matter could organize itself. Simulations, after all, are not crystal balls. They are controlled experiments built atop approximations. They rely on adjustable parameters, star formation efficiency, feedback strength from supernovae, dust properties, black hole accretion behaviors, and must balance computational feasibility with physical fidelity. It is no insult to theory that its predictions faltered in places. The early universe operates in regimes difficult to calibrate from lower redshift observations. As soon as JWST's surprising results emerged, theorists began the meticulous process of revising inputs, expanding model resolutions, and testing new physical prescriptions. The first changes targeted selection effects, the quiet culprits behind many observational surprises. Selection effects occur when telescopes preferentially detect objects with certain characteristics, brighter, redder, or more compact sources, while overlooking others that are equally important but harder to spot. In the context of JWST, its sensitivity to infrared wavelengths meant it could pick up galaxies whose colors were significantly influenced by emission lines or dust. These objects, rare in earlier datasets, weren't necessarily indicative of the average early universe. They were simply the ones most visible. Once simulations were adjusted to include these biases, the apparent mismatch between prediction and observation began to soften. A similar pattern unfolded with early mass estimates. Some galaxies initially appeared to be implausibly massive for their epoch, sparking public fascination with the notion that something fundamental might be broken. But as theorists updated simulations to account for the contribution of emission lines to observed brightness and added realistic models for dust reddening and compact star formation, the theoretical predictions began to align more closely with the revised measurements. The shock headlines faded not because observations diminished in significance, but because theory learned to speak the same language as the data. One of the most important developments was the incorporation of burst-driven star formation into early universe models. Previously, simulations assumed a relatively smooth pace of star birth, punctuated by only occasional intense episodes. But the extraordinary brightness of certain early galaxies suggested that the cosmos may have favored rapid, concentrated bursts of star formation, driven by dense gas flows and high merger rates. When theorists incorporated these possibilities into new models, sudden early luminosity became less surprising. Likewise, improved simulations of gas inflow and cooling at high redshift showed that early galaxies could collapse more quickly than expected, particularly in regions where dark matter halos were dense and closely clustered. These conditions created natural funnels of material, allowing galaxies to assemble in accelerated phases that matched the luminous populations JWST observed. All of this highlighted an essential distinction. Tension is not contradiction. Tension is the space where theory and data do not yet match but remain compatible. Contradiction, in contrast, is where data outright violate theoretical expectations. JWST's discoveries did not contradict cosmology. They simply revealed processes operating at the productive extremes of what theory had permitted. Theorists responded not by abandoning models, but by refining them. The universe had spoken, and theory listened. This iterative dance between observation and simulation is not a failure. It is the core of scientific progress. Observations guide theory, theory informs new observations, and the cycle tightens understanding over time. JWST's results accelerated this loop dramatically, pushing simulations into territories they had not yet fully explored. Far from collapsing, theoretical cosmology became more vibrant, flexible, and attentive to the subtleties of early structure formation. In the months after the initial shock, a calmer narrative took hold across the field. The early universe was energetic, efficient, and capable of rapid assembly, but still entirely governed by known physics. The models hadn't been wrong so much as incomplete, shaped by assumptions calibrated in the relatively gentle cosmic environment of later epochs. The intense conditions at early times required new approaches, sharper tools, and more daring simulations. The result was a synthesis rather than a surrender, refined models that better reflect the vigorous creativity of the young cosmos. As simulations continue to evolve, they will almost certainly find new ways to reproduce the remarkable populations JWST revealed, galaxies that form early, shine brightly, and behave with a confidence that once startled observers. And in doing so, theory will not merely catch up to observation. It will lay the groundwork for interpreting the next surprises the universe has already prepared, waiting patiently for a telescope sensitive enough to notice. Chapter 13. The Firefly, Sparkle, and the Art of Assembly. There is a particular stillness that comes from observing a galaxy not as a polished, swirling system, but as a collection of luminous fragments, a structure caught mid-assembly, with its scaffolding exposed and its future shape only faintly suggested. In most cases, galaxies in the early universe appear as blurred smudges, almost too distant for their internal components to be resolved. They are like silhouettes glimpsed through a foggy window, recognizable in outline, but missing their intricate interior details. Then came Firefly Sparkle, a galaxy whose appearance was sharpened by the gravitational magnification of a massive cluster in the foreground. Instead of a fuzzy glow, JWST revealed something far more intimate, a set of brilliant star clusters gleaming like fireflies in a dark meadow, each one a compact pocket of intense activity. The nickname Firefly Sparkle captures this improbable clarity. 10 discrete knots of starlight scattered across a galaxy barely 600 million years removed from the Big Bang. In this case, the magnification acted like a cosmic magnifying glass, bringing into focus a structure that would otherwise have been too tiny to discern. The galaxy's redshift, Z equals 8.296, places it at a time when the universe was just beginning to settle from its earliest storms of formation. Yet it already contained 10 dense star clusters, each hosting hundreds of thousands to millions of stars. Remarkably, together, they made up almost half of the galaxy's total stellar mass. This is an astonishing distribution. In mature galaxies, mass tends to be spread over spirals, bulges, and diffuse regions. But here, mass was concentrated in discrete, tightly packed islands of starlight. Each cluster was gravitationally cohesive, brilliant, and distinctly structured, suggesting that the galaxy had not yet blended into a smooth whole, but was instead stitched together from powerful local engines of star formation. It's a bit like witnessing a city being built, not from a sprawling blueprint, but from 10 bustling neighborhoods springing up independently, each burning with activity, each vibrant in its own right, and each eventually destined to merge into a coherent metropolis. For astronomers accustomed to studying galaxies as integrated systems, this site felt like stepping onto the construction site itself. The Firefly Sparkle was not a finished work of cosmic architecture. It was a mosaic of star-forming complexes, each one carving out its place in the larger structure. Instead of admiring the final building, we were finally seeing the workers, the scaffolding, and the materials still mid-assembly. These clusters were not gentle environments. The high densities required to pack that many stars into such compact volumes imply extremes of pressure, temperature, and turbulence. A radiation from newly formed stars would have blasted into the surrounding gas, shaping the next waves of star formation while carving small cavities in the medium. This energetic interplay, compression, heating, collapse, and feedback formed a rhythmic heartbeat at the center of the firefly sparkle's evolution. What the telescope revealed was a process long predicted but rarely observed directly. That early galaxies often grow from the merger and interaction of star clusters, not from smooth, gradual condensation. The clusters, still young, would eventually dissolve slightly, spreading their stars into a more unified structure. Others might collide or interact gravitationally, forming the spine of the galaxy's future architecture. The galaxy we see today, fractured into 10 glittering points, was a snapshot of this complex choreography. This cluster-dominated view of early galaxy growth carries profound implications. It suggests that some of the universe's earliest stellar populations did not arise in diffuse rotating disks, but in intense, compact factories, places where stars were born with remarkable efficiency. Conditions like these might have given rise to the first globular clusters or produced environments conducive to forming the seeds of early black holes. Although this chapter of cosmic history was full of violence and energy, it produced structures capable of enduring for billions of years. It also hints at why early galaxies appeared so bright in JWST observations. If their stellar mass is concentrated in dense clusters rather than spread across large volumes, their luminosity can be disproportionately high. These clusters act like cosmic beacons, their concentrated starlight punching above its weight in distant data. But beyond the technical insights, there is something quietly moving about seeing a galaxy in this embryonic state. It feels less like studying a distant foreign system and more like watching the cosmos learn how to build. The firefly sparkle does not present itself as a grand spiral or a regal elliptical. It offers the raw materials of such forms. It shows the universe not at a moment of completion, but at a moment of becoming. Each cluster is a chapter in that becoming, a flash of brilliance contributing to a story still unfolding. The magnification that brought this galaxy into view served as an invitation to step into an ancient workshop, one whose tools were gravity and gas, whose workers were the forces of collapse and radiation, and whose product would someday be a fully formed galaxy drifting through space with quiet confidence. Observing the firefly sparkle is like turning a page backward in cosmic history and finding not a polished narrative, but a draft full of energy, promise, and unrefined structure. It is a reminder that galaxies are not born whole. They assemble themselves piece by piece, cluster by cluster, in a slow and spectacular process that JWST has only just begun to unveil. It is the art of assembly, seen from the inside, and in its light, we witness not a finished universe, but one still learning the craft of creation. Chapter 14. The universe builds in neighborhoods. If one imagines the early universe as a vast, silent expanse dotted with lonely islands of starlight, the mental picture feels poetic, but deeply misleading. For years, even astronomers leaned on this imagery. tiny galaxies forming timidly in isolated pockets of primordial space, separated by great stretches of emptiness as they gathered gas and starlight at their own leisurely pace. It was a comforting interpretation, one that made the earliest structures feel fragile, tentative, and rare. But the more we peer into cosmic dawn, the more that picture dissolves. The universe, it turns out, was not a lonely frontier. It was a bustling neighborhood under construction. Many of the earliest galaxies detected by JWST have revealed nearby companions, sometimes faint and sometimes surprisingly bright, clustered like small villages taking shape along the same cosmic river. In some deep fields, sources appear in pairs or trios, separated by distances that in cosmic terms might as well be adjacent houses. Their light, spread across billions of years of travel, converges on our detectors with a subtle synchrony. Different voices speaking at nearly the same moment in cosmic time. These companions are not incidental. They are gravitational partners, shaping one another's fates in ways both gentle and dramatic. Even in their infancy, galaxies seemed drawn toward collaboration. Instead of drifting alone across the emptiness, they grew in dense pockets where dark matter pooled into halos, structures that drew in gas and smaller neighbors. Gravity, the universe's great social organizer, encouraged these galaxies to mingle, merge, and exchange material. The result was less a scattering of lonely pioneers and more a collection of early cosmic cities, where interactions were frequent and evolution was communal. It is in these busy neighborhoods that galaxies learn to grow quickly. Mergers, often portrayed as violent collisions, were, in the early universe, acts of creative construction. When two galaxies interacted, their gas clouds compressed, igniting starbursts. Their structures intertwined, redistributing mass, momentum, and heavy elements. Their mutual gravity sculpted new shapes, blending their identities into larger, more complex forms. There is something deeply organic about this process. One can picture these early galaxies not as rigid objects, but as soft, malleable gatherings of stars and gas, malleable enough to reshape themselves with each encounter. Their interactions weren't catastrophic. They were formative. The universe, still warm with youth, allowed for collisions that built rather than destroyed. In many JWST fields, the evidence of these cosmic neighborhoods appears as faint smudges adjacent to brighter cores, companions lurking at the edges of detection. Some are stretched by tidal forces, elongated like threads pulled from a larger cloth. Others appear nearly intact, as though waiting patiently for their moment of gravitational entanglement. Still others seem midway through merging, their light profiles blended into delicate asymmetries. These snapshots tell a story of rapid assembly, a kind of accelerated urban development playing out under the laws of gravity. We are witnessing the earliest blueprints for galaxy clusters, the prototypes of the grand structures that dominate the universe today, where later epochs show sweeping clusters with hundreds of members. The early universe offers their intimate origins. Tiny groups gathered together, all learning how to share mass and momentum. And this is the critical realization. Isolation was the wrong mental image all along. Galaxies did not emerge in solitude. They were born into networks of structure defined by dark matter filaments, long invisible threads stretching across space, funneling gas and small halos into intersections where galaxies bloomed in clusters. even at epochs when the universe was only a few 100 million years old, these filaments orchestrated the movement of matter, encouraging galaxies to meet, merge, and morph. Cosmic dawn was therefore not a quiet whisper. It was a chorus of interactions. Each galaxy's growth was influenced by the proximity of neighbors, some merging outright, others merely tugging at one another in passing, nudging trajectories and compressing gas clouds. A single encounter could alter a galaxy's future, triggering star formation or redirecting its flow of material. One can imagine the universe like a young city developing along natural pathways, waterways on Earth, filaments in space. Settlements form at intersections because the terrain encourages it. Likewise, galaxies congregate where dark matter deepens the gravitational landscape. None of this required intention. It was the natural consequence of physics guiding matter along the paths of least resistance. What JWST has revealed is the texture of this early social structure, not the broad strokes implied by older observations, but the fine details, the subtle gravitational whispers between neighbors, the faint imprints of tidal interactions, the traces of mergers in embryonic stages. Each detection adds depth to the realization that the universe was never as empty as it once seemed. And perhaps there is something quietly humorous in this revelation. Astronomers spent decades anticipating faint, lonely galaxies barely clinging to existence at the edge of visibility. Instead, they found something closer to an early cosmic block party. Galaxies huddled together, sharing gas, exchanging stars, and growing more rapidly as a result. This understanding reshapes not only our view of individual galaxies, but also the grand architecture of the cosmos. By recognizing the importance of neighborhoods, of clustering, companionship, and interaction, we begin to see galaxy formation as a communal process, not a solitary endeavor. The universe builds in groups because gravity rewards proximity. Growth is faster, brighter, and more dynamic when galaxies evolve side by side. In the deep past, the cosmos was not empty. It was collaborative. It was alive with interactions that shaped every structure we see today. And in observing those early neighborhoods, we glimpsed the universe not as a collection of isolated points, but as an interconnected web, one that began weaving itself long before the first galaxies took their final forms. Chapter 15. The Human Side of Cosmic Discovery. There is a particular quiet that settles over a research office late at night, the kind filled not with darkness, but with the pale glow of monitor screens, the soft shuffle of notebook pages, and the steady hum of cooling fans. It's in spaces like these that some of the most profound cosmic realizations first take shape. Not in grand press conferences, not in dramatic announcements, but in the private stillness where a scientist leans closer to a graph, looks twice, and feels the subtle shift of an idea rearranging itself. When JWST's earliest findings began to emerge, the universe revealed a version of itself that advanced with startling confidence. Galaxies forming earlier than expected, black holes lighting up before galaxies themselves had fully taken shape, ionized bubbles appearing in places still thought to be thick with primordial fog. Each result nudged the boundaries of familiar theory, but these revelations did not arrive as polished insights. They arrived as raw data, puzzling patterns, and unexpected peaks in the spectra. And for the researchers encountering them, the experience was profoundly human. Some of the earliest reactions came not as exclamations of triumph, but as long silences. A scientist might open a data set expecting a routine photometric check, only to find numbers that force them to pause, quietly, cautiously, before reaching for the nearest calculator. It is in these moments that one learns something essential about astronomy. Discovery often begins as disbelief whispered inwardly, never aloud. As the patterns repeated across independent data sets, the disbelief shifted into a more urgent form of curiosity. Many researchers found themselves recalculating parameters late into the night, trying to understand whether the numbers were leading them astray or leading them somewhere entirely new. There were quick messages sent to collaborators, carefully phrased, equal parts excitement and hesitation. Can you check this? Does it look right to you? This is the emotional rhythm of modern astronomy, a gentle oscillation between doubt and wonder. Meanwhile, the practical consequences began to ripple outward. Conference presentations prepared months in advance suddenly felt out of date. Slides showing predicted galaxy counts or expected brightness ranges now sat awkwardly beside new data that refused to behave. Researchers rewrote introductions to talks, revised models overnight, and added last-minute footnotes acknowledging results that were still too new to fully interpret. Paper drafts, once leisurely documents that evolved over months, suddenly needed urgent rethinking. Sections describing rare early galaxies were revised to acknowledge that they might not be rare at all. Abstracts that assumed certain formation rates were rewritten in a softer tone, the language shifting from confident assertion to measured possibility. For many astronomers, this period carried an emotional whiplash, the thrill of unprecedented discovery mixed with the humility of watching long-held assumptions dissolve. It is one thing to suspect that the early universe might be richer than expected. It is quite another to see the evidence flickering on your screen in pixelated detail. Yet, despite the intensity of this moment, the atmosphere was not one of panic or defensive caution. Instead, it was contemplative, almost reverent. Those working closest to the data spoke of feeling as though they were witnessing something intimate. Structures and processes that had existed since cosmic dawn but had never been seen with clarity. The universe wasn't rewriting its story. It was allowing humanity to read an older chapter for the first time. There were also lighter moments, the kind that revealed the humanity beneath the science. Some researchers joked about editing the universe or filing a bug report with reality. Others admitted to blinking repeatedly at the screen, convinced that the numbers might behave differently if observed with enough skepticism. The humor was gentle, born not from frustration, but from the shared recognition that the cosmos had once again outpaced expectations. These discoveries also reshaped the way collaboration felt. Emails multiplied across time zones, video calls stretched into odd hours, and scribbled diagrams circulated like secret letters. Scientists who had never met in person found themselves united by the same puzzling data, bonded by the shared exhilaration of uncovering something profoundly new. Their conversations carried the tone of explorers comparing notes at the edge of a continent no map had yet charted. And beneath it all was a kind of quiet gratitude. Astronomy is full of moments spent waiting for observations, for clear skies, for funding cycles, for code to compile. But these results reminded everyone why the waiting is worthwhile. The universe, in its vast patience, had been storing its earliest secrets for billions of years, revealing them only when the tools and timing aligned. To be the first generation with the sensitivity to see these distant structures is not merely a scientific privilege. It is an emotional one. It transforms the abstract into the tangible. It turns numbers into narratives, spectra into stories. The human side of cosmic discovery is not measured in data points or redshifts. It is measured in the subtle shifts of understanding, the quiet rewrites of familiar lectures, the realization that models must bend, reflections deepen, and curiosity expand. It is the recognition that learning about the universe is not a march toward certainty, but a dance between expectation and revelation. And as researchers absorbed these early surprises, a shared sentiment grew. Not fear, not confusion, but a renewed sense of wonder at a universe that seems determined to stay just beyond the edge of what we think we know, revealing itself not all at once, but in soft, expanding circles of light. Chapter 16. When headlines run faster than data. When the first JWST discoveries reached the public sphere, they arrived not as quiet scientific notes, but as proclamations. Headlines burst across screens with the urgency of breaking news, many of them declaring that the foundations of cosmology had cracked or shattered or been flung unceremoniously into the void. Words like impossible, unprecedented, and unexplainable were embedded in every other headline, painting a picture of a universe so unruly it had apparently staged a rebellion during early JWST observations. The drama was compelling, of course. Few phrases generate clicks faster than "cosmology is broken," especially when paired with evocative images of the deep universe. But within the scientific community, the reaction was noticeably more tempered, less panic, more eyebrow-raising. Researchers knew that the universe rarely jumps away from its governing laws without warning. Yet it evolves, it surprises, it nudges our expectations, but it does not tend to break. The discrepancy between public excitement and scientific caution is not a new phenomenon. Astronomy, with its sweeping vistas and profound implications, lends itself easily to narrative exaggeration. The early JWST data simply provided a fresh supply of raw material for enthusiastic interpreters. But these headlines also revealed something deeper, a tendency to mistake scientific tension for scientific crisis. Tension is the normative state of scientific progress. It is the uneven ground where new data challenge old models, where uncertainty grows before understanding catches up. But crisis, true crisis, is rare. The laws of physics are not fragile. They have survived centuries of scrutiny, refinement, and even complete reimagination. When a telescope reveals something unexpected, scientists do not leap to declare that gravity has quit or that the Big Bang has been rendered obsolete. They look closer, adjust models, refine interpretations, and expand the boundaries of what simulations attempt to capture. Yet in the first months of JWST's operation, this nuanced process was often overshadowed by waves of rapid reporting. Articles circulated claiming that massive galaxies observed in the early universe had no place in current theory. Comments circulated suggesting that dark matter might be in trouble, or that the speed of galaxy formation had been catastrophically underestimated. Readers were left with the impression that astrophysicists were scrambling to rewrite the first chapters of cosmic history. But that was never the case. What actually happened behind the scenes was slower, quieter, and far more productive. As follow-up work accumulated, many of the dramatic claims softened. Early mass estimates, once thought to imply impossibly massive galaxies, were revised when emission line contributions, dust effects, and photometric biases were properly accounted for. Galaxies once described as monsters became simply brighter than expected, not beyond reason, not beyond physics, just more efficient in their star formation than previously believed. Similarly, early redshift estimates were fine-tuned. Some of the most dramatic candidates, touted as record-shattering, turned out to be closer than initially estimated once spectroscopy began filling in the details. This was not a failure, but the natural progression of data refinement. Photometry is a map. Spectroscopy is the compass. One shows direction, the other locks in the coordinates. As these revisions emerged, the tone within academic circles remained steady. Papers referenced the early uncertainties with clarity, but without alarm. Conference presentations unfolded with an emphasis on new models, not discarded ones. The narrative shifted organically from astonishment to insight, from headline-ready shock to the calm work of understanding. This is why slow science remains not only healthy, but essential. Fast science, science forced to perform on a public stage before it has matured, can generate unnecessary controversy, inflate misunderstandings, and flatten the subtlety that makes real discovery meaningful. Slow science, by contrast, allows ideas to ferment. It invites collaboration, skepticism, and iteration. It fosters humility, the quiet recognition that first impressions are often incomplete and must be held lightly until the evidence grows. When headlines run faster than data, the pace mismatches the process. The public sees crisis where scientists see opportunity. The universe appears unstable when it is merely unfamiliar. And the careful, meticulous work of interpreting cosmic signals risks being overshadowed by the immediacy of speculation. Yet there is also something endearing about this cycle. It reveals how deeply people care about the cosmos. The eagerness to interpret new data, sometimes too quickly, is a testament to the universal human desire to understand our origins. The challenge lies not in dampening this enthusiasm, but in guiding it gently, creating space for both excitement and patience. Scientists do not resent the headlines. They simply live on a different timeline. They move at the speed of careful reasoning, at the pace of peer review, at the rhythm of nights spent refining equations and rerunning models. Discoveries for them unfold like slow dawns, not sudden fireworks. And so, as JWST's early surprises settled into clear interpretations, the story became richer rather than less dramatic. The universe did not break. It revealed new textures. It didn't contradict itself. It expanded our understanding of the possibilities contained within its earliest epochs. The headlines eventually quieted, but the science continued, steady, curious, and unhurried, just as it has always been. Chapter 17. What didn't break after all? For all the excitement surrounding JWST's early discoveries, the luminous galaxies, the compact starbursts, the early black holes, and the patchy reionization, one truth slowly, quietly reasserted itself. The universe, despite its flair for surprise, had not violated its own rules. Our cosmological framework, anchored by the Lambda CDM model and shaped by decades of theoretical and observational work, remained standing. It may have shifted its weight, stretched its limbs, and revealed unexpected flexibility, but it did not buckle. This outcome was less dramatic than some early headlines predicted, yet far more scientifically meaningful. It showed that the cosmos is robust, not fragile, dynamic, not erratic. And it reminded astronomers that the most enduring frameworks are those capable of absorbing new information without losing their structural coherence. At the center of this resilience lies lambda CDM, the model that describes a universe dominated by dark energy, lambda, and cold dark matter, CDM. For years, it has served as the backbone for simulations of cosmic evolution, guiding predictions about structure formation, galaxy clustering, and the growth of large-scale filaments. It would have been easy to suspect that JWST's glimpses into the earliest epochs, where galaxies appeared earlier and brighter than anticipated, might challenge this foundation. But the opposite happened. As the observations accumulated, lambda CDM showed itself to be remarkably capable of accommodating the newly revealed complexity. It required adjustments, certainly, but these adjustments lived comfortably within the model's flexibility. They were refinements, not replacements. One of the most visible areas of refinement involved star formation efficiency. Earlier models tended to assume relatively modest efficiency in the first few 100 million years, predicting that galaxies should start small and faint. JWST, with its sharper view, revealed that star formation in certain early galaxies was far more effective than assumed, able to convert gas into stars at a brisk and enthusiastic pace. But this was an adjustment to assumptions, not a contradiction of cosmic law. Increasing star formation efficiency within simulations does not break lambda CDM. It simply populates the early universe more richly. A galaxy forming stars at 10 times the expected rate may be surprising, but it does not violate gravity, thermodynamics, or the behavior of dark matter halos. It simply suggests that the interplay between cooling gas, turbulence, and feedback was more favorable to rapid star birth in some environments than previously modeled. Another area of refinement involved feedback processes, the ways young stars and black holes inject energy into their surroundings. Early universe conditions may have allowed feedback to behave differently from later epochs, either by compressing gas more dynamically or by clearing pockets that accelerated subsequent collapse. This too fits within existing physics. If anything, it highlights how much of galaxy evolution depends on local environmental conditions rather than universal constants. Even the appearance of unexpectedly early black holes did not defy lambda CDM. The possibility of heavy seeds, introduced in earlier chapters, is entirely compatible with dark matter-driven structure formation. If dense early halos collected gas efficiently enough to trigger direct collapse events, then massive black holes appearing at redshifts around 10 or higher make sense. They are evolutionary outcomes of extreme but permissible conditions. One of the most reassuring aspects of these refinements is that they emerged naturally from iterative modeling. As theorists incorporated more realistic assumptions, stronger early cooling, burstier star formation, compact stellar clusters, they found that many of JWST's unexpected galaxies became straightforward to reproduce. The simulations did not require exotic forces, altered constants, or new particles. They simply required a better approximation of how ambitious the young universe could be when given ample gas and dense gravitational wells. This adaptability underscores an important distinction. Science bends before it breaks. A robust theory is not one that predicts every detail in advance, but one that remains coherent when unexpected details appear. Lambda CDM did not predict the exact brightness of the earliest galaxies, but it predicted a universe where such galaxies could exist, provided the internal physics was tuned correctly. What truly remained unshaken was the dark matter framework. JWST's revelations reinforced the idea that early structure formation depended heavily on dense dark matter halos drawing gas inward. Early clustering, rapid mergers, and starburst pockets all emerged in environments shaped by dark matter's gravitational influence. These features are not anomalies. They are evidence that the fundamental scaffolding of the universe behaved exactly as the model predicted. Likewise, the universe's large-scale geometry, expansion history, and matter composition remained consistent with established understanding. There was no sign of altered inflation models, no need to discard dark energy, no evidence of exotic departures from standard physics. The cosmos, in its earliest visible epoch, was energetic and efficient, but still played by the gravitational rules we know. Perhaps the most profound lesson from all this is how science absorbs surprise. The early universe was brighter and busier than expected, but this only revealed that the space of possibility was wider than previously imagined. The model expanded to accommodate new observations, not by force, but by natural flexibility. Lambda CDM is not a rigid monument. It is a living framework, capable of growing in resolution and nuance. In this chapter of cosmic understanding, nothing snapped. Instead, theories stretched, adjusted, and found room for new phenomena. The universe, in all its youthful exuberance, simply encouraged us to broaden our expectations. And so, what didn't break after all was not just cosmology. It was our trust that the universe, however surprising, remains fundamentally intelligible. Chapter 18. A universe that grew up too fast. There is a familiar story we often tell ourselves about beginnings. We imagine them as slow, tentative, and delicate, moments defined by hesitation rather than momentum. The earliest universe, long portrayed in this gentle way, it was assumed to be a place where cosmic structures took cautious first steps, learning how to assemble stars and galaxies with the steady patience of a child discovering balance. But the picture emerging from JWST's deep view observations suggests something quite different. A universe that raced through its formative years with startling ambition, assembling stars, galaxies, and black holes at a pace that rivals or exceeds activity in much later epochs. This wasn't a hesitant dawn. It was an energetic sprint. The earliest structures did not drift gently into existence. They ignited, condensed, merged, and flourished with remarkable efficiency. At every observational turn, the signs point toward a cosmos that was capable of organizing itself far faster than anyone had confidently predicted. Early galaxies shone with unexpected brightness. Star formation erupted in compact clusters. Black holes fed with fervor, and ionized regions carved their way through primordial hydrogen long before models anticipated. It leaves the impression of a universe that entered its adolescence while still an infant, skipping some of the slow developmental stages we assumed were mandatory. This rapid assembly is not a single phenomenon, but a tapestry woven from many threads. Among the most striking is the efficiency of early star formation. conditions in the first few 100 million years favored the rapid collapse of gas. Densities were higher, temperatures cooler in the right pockets, and turbulent flows more intense. Rather than forming stars in leisurely drizzles, many early galaxies appear to have ignited in bursts, creating compact or brilliant clusters that contributed disproportionately to their luminosity. Where later galaxies often stretch star formation across wide disks, the earliest ones packed their young stars into tight regions, creating dazzling pockets of clustered activity. These conditions likely amplified the universe's ability to produce light early on. The combination of compactness and intensity meant that even modestly sized galaxies appeared as cosmic beacons. The brightness that once puzzled astronomers now seems less a sign of anomalous mass and more a signature of tightly concentrated star factories working at peak efficiency. Parallel to this stellar vigor was the swift rise of black holes. Some early galaxies harbored accreting black holes so young and yet so energetic that their presence forced researchers to consider new formation pathways. Heavy seeds and rapid gas inflows may have allowed these black holes to grow in tandem with their host galaxies, rather than lagging behind by hundreds of millions of years. Instead of waiting for star cycles to produce remnants that might eventually collapse into black holes, the universe may have jumped directly into forming massive seeds capable of rapid accretion. These black holes, by feeding and radiating strongly, likely influenced the very environments that nurtured them, heating nearby gas, stirring turbulence, and shaping star formation patterns. In the earliest epochs, the separation between galactic structure and black hole activity grows faint. The two processes seem intertwined, each accelerating the other. Yet perhaps the most transformative shift in perspective comes from realizing just how interconnected early structures were. Galaxies formed in neighborhoods rather than isolation, drawing gas from shared filaments, merging with nearby companions, and triggering new waves of star formation through interactions. Instead of quiet, solitary growth, early cosmic history resembles a crowded, cooperative marketplace, where every encounter exchanged energy and accelerated development. This fast-paced environment challenges earlier assumptions about how long it should take for galactic disks to stabilize, for black holes to emerge, for stellar populations to diversify, or for ionized bubbles to carve paths through hydrogen fog. The standard cosmic timeline was not overturned. It was simply revealed to have more flexibility than previously recognized. Some galaxies may have grown slowly and gently, but others grew aggressively, taking full advantage of the early universe's fertile conditions. These revelations invite a reframing of cosmic dawn itself. Instead of picturing a quiet morning where light seeped gradually into the darkness, it becomes more appropriate to imagine the first few 100 million years as a storm of creative activity, brilliant, uneven, and exuberant. The universe wasn't tentative, it was industrious. It wasn't fragile, it was deeply capable. It didn't wait for equilibrium, it built toward it at top speed. Such an energetic early universe does not contradict cosmology. It enriches it. It reveals that the cosmos has multiple tempos, multiple strategies, multiple pathways for building structure. The slow-growing galaxies we observe at later times do not negate the existence of early overachievers. Diversity, rather than uniform pace, becomes the signature of cosmic evolution. The implications are far-reaching. They affect our understanding of how galaxies mature, how the first heavy elements distributed themselves, how black holes influenced their hosts, and how long it took for the universe to become transparent. The early cosmos becomes less a blank canvas waiting to be painted and more a bustling workshop already filled with tools, raw materials, and half-built structures. And in this new view lies something quietly profound, the recognition that the universe from its earliest moments possessed an astonishing degree of competence. It did not need billions of years to become dynamic. It was dynamic from the start. A universe that grew up too fast is not one that defies explanation. It is one that expands our understanding of what is possible. It encourages scientists to refine their models, deepen their simulations, and revisit long-held assumptions with renewed curiosity. It whispers the reminder that the cosmos is always a little ahead of us, unfolding at a pace that invites awe but requires patience to comprehend. In this light, cosmic dawn becomes not the timid beginning of a long story, but a vibrant overture, rich, complex, and full of flourishing energy from its very first notes. Chapter 19, The Questions Webb Was Never Supposed to Ask. Every great instrument is built with a set of intentions, carefully crafted goals, design requirements, all hand performance expectations that guide its creation. The James Webb Space Telescope was no exception. Engineers and scientists spent years defining the parameters of what it should achieve, measuring distant galaxies, analyzing exoplanet atmospheres, tracing star formation through dust, and observing the faint glow of structures from cosmic dawn. What no one fully anticipated, however, was how many questions the telescope would raise that were never included anywhere in those original plans. Webb has become the kind of observatory that reveals not only answers, but also entire categories of phenomena that scientists had not known existed. Puzzles that emerged simply because we finally built a tool sharp enough to expose them. It is the cosmic equivalent of cleaning a window only to discover an entire landscape you didn't know was hiding behind the glare. The telescope was designed with a clear scientific vision, but its extraordinary sensitivity and resolution mean that it sees details the human imagination never fully prepared for. In many ways, Webb's most transformative discoveries have been side effects of looking carefully, unintended revelations that sprout in the corners of images, or whisper their presence through delicate spectral signatures. This is the paradox of advanced observation. The more precisely you try to illuminate what you expect, the more brightly you reveal what you never imagined. Take the little red dots, the compact, intensely red objects that appeared across deep field images like scattered embers. Our Webb wasn't launched to search for such a population. It simply had the sensitivity to detect faint red light that previous telescopes would have dismissed as background noise. The dots slipped into the data quietly, not as targets, but as consequences of the instrument's capability. They were discovered because JWST looked deeper than ever before, not because anyone predicted they would be there. Similarly, some early black hole signatures emerged not from dedicated AGN surveys, but from broad spectroscopic sweeps meant to understand star formation. The high ionization lines hidden in some spectra were like voices in a room that had always been present but never audible until the microphone became sensitive enough. JWST was not built exclusively to rewrite black hole formation theories. Yet it nudged astronomers into that conversation anyway. This pattern repeats itself across multiple discoveries. Webb's deep NIR-CAM images, meant to map early structures, ended up revealing star clusters inside forming galaxies. Not because cluster-scale resolution was the mission goal, but because gravitational lensing happened to combine with JWST's clarity in precisely the right way. What began as routine imaging became a glimpse into the construction materials of galaxies themselves. Even the evidence for patchy rionization was not part of a direct experiment. Webb observed distant galaxies, and in their spectra, scientists noticed Lyman alpha photons escaping from epochs where they shouldn't. Instead of confirming a smooth cosmic transition, the data whispered of complex ionized bubbles, small local pockets of clarity that no earlier instrument could have isolated. It wasn't that researchers didn't want to know how reionization unfolded. They simply never expected to see it in such fine detail. This is the subtle magic of Webb. Its design intent was broad, but its sensitivity is surgical. In increasing observational precision, we open room for new questions, not because the universe changes, but because our understanding becomes more detailed. Many features that JWST has exposed were always part of cosmic history. They were simply too faint, too small, or too swift to capture before. The telescope acts not as a revolution, but as a revelation, peeling back layers of approximation to show what the universe has been doing quietly all along. This is not a failure of planning. It is an invitation. The universe observed with higher fidelity becomes less a static backdrop of long-known processes and more a dynamic space full of surprises. New structures appear between pixels once assumed empty. Spectral lines hide secrets inside shapes once thought featureless. Even the silence, regions where no galaxies appear, becomes meaningful when seen with enough clarity. Webb forces us to confront something fundamental about discovery, that questions often arise not from gaps in knowledge, but from new abilities to perceive. When instruments evolve, the universe reveals new contours. When resolution sharpens, categories expand. When sensitivity deepens, nature introduces itself again. More complex, more nuanced, more intricate than before. The story of JWST is therefore not simply one of achieving goals, but of transcending them. Its impact lies in making the unknown unavoidable. The telescope has uncovered phenomena no committee anticipated and no model predicted. Not because those models were flawed, but because the universe had more to say than our earlier tools could interpret. This forces a quiet reflection on the nature of scientific inquiry. We often imagine discovery as a march toward clarity, a disciplined progression from mystery to understanding. But Webb shows that discovery also flows in the opposite direction, from understanding into deeper mystery, from answers into better questions. It teaches us that progress is not a narrowing of curiosity, but an expansion of it. The greatest surprises do not come from staring at the unknown, but from staring at the familiar with new precision. In the end, the telescope reveals a universe that was never simple, never static, and never confined to the boundaries of our imagination. It was always ready to surprise us. All it needed was an instrument capable of noticing the details, the faint whispers, the subtle deviations. And so JWST asks questions it wasn't designed to ask. because those questions were always waiting in the starlight, patient as only the cosmos can be until the moment a sensitive enough eye finally opened. Chapter 20, The Calm Realization. Across all the surprise, revision, wonder, and reinterpretation sparked by JWST, a softer truth emerges, one that settles into the mind like dusk settling across a quiet landscape. The early universe, for all its brilliance and energy, was not rushing. It was not frantic or chaotic or strained. It was simply efficient, moving according to laws that had been in place since the first fractions of a second after the Big Bang. What feels fast to us is only unfamiliar. What seems surprising is, in hindsight, deeply natural. This realization arrives slowly, almost shyly, as if the cosmos were guiding us away from our initial astonishment toward a gentler understanding, that the universe did not grow up too quickly. It grew exactly as its conditions allowed. Efficiency is not haste. In the early cosmos, densities were high, gas was plentiful, and temperatures were poised at a delicate balance that encouraged rapid collapse. Under such circumstances, matter had little reason to linger or delay. Gravity was assertive. Cooling was swift in the right pockets, and the raw materials of creation were everywhere. Star clusters kindled in compact knots. Black holes took advantage of deep wells of gas, and galaxies found neighbors easily along dark matter filaments that had already begun to shape the cosmic web. It feels fast to us only because we are accustomed to a quieter, more diffuse universe, the one we inhabit now, where expansion has stretched space into a gentle dilution and where energy is dispersed across great distances. But in those early epochs, the cosmic environment was richer, more intimate. Creation was not hurried. It was simply abundant. The more astronomers sift through JWST's data, the more they see this pattern reflected everywhere. Bright galaxies do not violate the rules of structure formation. They express them. Black holes do not emerge impossibly early. They arise from natural pathways that were always available under the right conditions. Patchy Ryanization is not a disorderly exception. It is the expected outcome of localized brilliance, illuminating its surroundings in a staggered rhythm. Even the oddities, the little red dots, the concentrated clusters in firefly sparkle, the unexpectedly vigorous neighborhoods become less startling when viewed through this calmer lens. They are variations within a system that favors diversity. The universe at that time was experimenting freely, not waiting for instructions, using whatever combinations of gas, gravity, and radiation were at hand. It was learning how to build complexity with the eagerness of a young artist surrounded by fresh materials. And perhaps this is what makes the calm realization so profound. The early universe was not striving toward some predetermined form. It was not rushing to assemble galaxies before a deadline or racing to ignite stars before its window of opportunity closed. It was simply relaxing into physical laws that naturally led to efficient outcomes. Patterns emerged because conditions allowed them to. Structures grew because the environment nurtured them. There is a quiet grace in seeing cosmic history this way. It removes the breathless urgency from discovery and replaces it with a deeper appreciation of how seamlessly the universe has always operated. The fact that galaxies blossomed earlier than anticipated does not imply a universe acting out of character. It reveals a universe fully expressing itself long before anyone observed it. And when we step back, the narrative softens. The tension dissolves. we begin to see an arc that is neither shocking nor contradictory, but beautifully coherent. The cosmos contains eras of intensity and eras of calm, periods of rapid assembly and periods of gentle drift. The early universe was one of those vibrant chapters, full of heat and concentration, but it gave way to quieter epochs, the expansion stretching space into vast and tranquil distances. The galaxies that once blazed with clustered starlight now drift in mature forms. The black holes that fed eagerly now glow more softly or sit in relative silence. The bubbles of ionization that once carved through hydrogen fog now form part of the clear open space through which light travels freely to our telescopes. The universe has grown spacious and serene, but its early vigor remains written into every structure we see today. The same filaments traced by ancient light still guide galaxies. The same dark matter scaffolding supports clusters. The same principles of gravity and thermodynamics shape the rhythms of stars. In this continuity lies the calm realization. Nothing about the early universe is fundamentally foreign. It is simply a version of the cosmos we know, expressed under different conditions, more intimate, more energetic, but following the same quiet logic. There is no grand conclusion waiting at the end of this journey. The universe does not demand one. Its story continues, patient and unhurried, stretching across time with the same steadiness it has always held. Our understanding expands, but the cosmos remains itself, ancient, vast, efficient, and calm. And so this chapter closes not with certainty, but with quiet acceptance. The universe formed early structures not out of speed, but out of opportunity. It grew luminous not out of urgency, but out of abundance. And long before any eyes were there to witness it, the cosmos unfolded gently, following the contours of its laws, serene in the knowledge that it had all the time it needed.